Hello and welcome to the conversation. My name is Sarah and I am joined by Lisa and David, and behind us we've got Dada producing, and peeking back there is Jade. We will have her later on the show. But in news, we've got...
Will the Earth's magnetic field flip?
And
can sea pineapples revolutionize thin film coatings?
all right. And Jade has an interview with Dr. Helena Braga about the future of batteries. Okay, all that and more coming up on TMRO Science, Discovery 1.05. All right, before we get into the news, we want to give a huge shout out to our Escape Velocity citizens. These people contribute $10 per episode. In return, they get their name in all 3 segments of the show, exclusive access to our Escape Velocity Discord channel, and so much more. Every bit helps, and we wouldn't be able to continue making these awesome shows if it weren't for you. So for a complete list of rewards, or if you would like to become a citizen of tomorrow, head on over to patreon.com/TMRO. Okay. You were saying about the Earth's magnetic field. Let's hear it.
Yes. Will the Earth's magnetic field flip again? A new study published in PNAS answers that very question. The Earth's magnetic field is known to flip periodically throughout the millennia. This was discovered in the 50s and the 60s as Earth scientists began to magnetically map the ocean floor, and stripe patterns were discovered that eventually led to the widespread acceptance of plate tectonic theory. As the magma emerges from the fault, it solidifies as it contacts the cold ocean water. As it does so, all the magnetic particles of the magma, having lined up with the magnetic field, freeze in place, preserving the polarity of the field for that portion of the magma. Now, as the ocean floor was first mapped, a striped pattern emerged, and not only that, but it was symmetrical on both sides of the fault. This was the holy grail of plate tectonic theory. This is what really clinched it. What's more, you could trace the patterns back through time, since as you progressed along the ocean floor away from the fault, you are going back in time, and you can determine the ages of the flips by dating the rocks. A flip would mean that if you had a compass and used it after the flip, the needle would point south instead of north, or vice versa. Approximately, of course, since the magnetic poles do not line up precisely with the geographic. These reversals occur on an average of about every 200,000 years, but the actual time can vary considerably. It has been 780,000 years since the last flip, so according to the average, we are overdue. Now, since we have been monitoring the field strength in modern times, there has been a measurable weakening. This has led scientists to consider the possibility that the field could be approaching a flip, but realize that since we had never seen one before, we have been uncertain how they actually manifest themselves in detail. Enter the science of paleomagnetism. In a study published in the journal Proceedings of the National Academy of Sciences, on April 30th, Earth's magnetic field is probably not reversing. Researchers have discovered that the pattern of the Earth's field today is not very similar to patterns that have existed in the past when the field flipped or reversed. In today's field, we have what is called the South Atlantic anomaly. This is an area where the inner Van Allen belt comes closest to the Earth's surface due to geometrical realities concerning how the magnetic axis is oriented relative to the geographic axis. The belt dips lower here and is actually a problem for satellites. The Hubble does not operate when passing through this area, for example. The area of the anomaly has been seen to expand, indicated here by the field strength decreasing since its discovery in 1958, and is believed to be due to the continued weakening of the magnetic field's overall strength. So actually, to be more precise, the field can ultimately do 2 different things. The first is a reversal or a flip, as I previously described. The second thing is an excursion. This is where the field weakens and gets all scrambled up, and then it returns back to its previous orientation. So this map shows the Earth's magnetic field during two recent, geologically speaking, periods of the Earth's history. These field patterns discovered do not match what we are currently seeing today with the South Atlantic anomaly. Today's pattern more closely matches, and I quote from the article, in earlier times centered at 49 and 46,000 years ago. The field is comparable to today's field with an intensity structure similar to today's South Atlantic anomaly. These fields, which are strongly similar to our field today, did not go on to develop into an excursion or a reversal. This indicates that our current weakening field will eventually recover and not lead to an extreme event.
All right, good to know. Phew, that means our navigation on the planet is not in danger.
Right,
What would
like
happen if the Earth's magnetic field had flipped?
Like birds will be okay,
All
and
right.
all the animals that use the magnetic field will be fine, and for now, but eventually it's going to happen, but for now we're okay.
All right, and just so we know, the Van Allen belts, could you remind me those?
The Van Allen belts are areas in where the radiation gets trapped in the Earth's magnetic field around the Earth, and so they're areas of concentrated radiation.
All right, cool. Okay, and now, I have heard just now that there are such things as sea pineapples, and I'm really intrigued.
Well, yeah, I mean, sea pineapples, they actually are a thing, and new research that was published yesterday, May 4, in the journal Advanced Functional Materials, shows that sea pineapples may actually be the secret to improving the strength of thin film coatings. So what this research was looking at was sea pineapples, or their scientific name is tunicates, and they're marine creatures that are actually known as a pest around some parts of the world. But in some parts of the world, they're also eaten as a delicacy. People eat these things. But the researchers found that if the tunicates were processed by controlled acid hydrolysis, which just kind of means like breaking down using acid, the remaining compound are called cellulose nanocrystals, which I'm going to call CNCs from now on. And don't get that mixed up with like building stuff CNC machines. This is different. And so these cellulose nanocrystals, CNCs, could be used to strengthen thin films. And CNCs are not new. They can actually be made really easily from wood pulp waste left over from things like lumber and paper industries. And much research has actually looked into whether wood-derived CNCs could be the next big biological material with like similar properties to bone or ivory. And they were strong, but they just turned out to be too brittle if you just used the wood CNCs alone. And that's where tunicates come in to save the day. So all CNCs, whether they're made from wood or from tunicates, can form helical nanostructures when left to dry into a film. And helical just means spiral. Each individual nanofiber is like a stair in the staircase, and multiple fibers pile on top of each other to form the staircase, like you can see in the top left corner of that image there, labeled A. It's like a staircase. And so the researchers just started with a mixture of just wood CNCs, and they tested what happened when they added different amounts of tunicate CNCs. They got these really striking patterns that are characteristic of staircase-shaped molecules when they looked at them under the microscope. But they also found that a mixture of about 30% tunicate CNCs combined with wood CNCs had the most strength. Each of the images that you can see here, below the below 6 images show an out-of-plane ductility test, or basically how much you can bend it before the film breaks. And each colored line there was the amount of curvature before the film snapped. But the researchers also found that mixtures greater than 10% tunicate CNCs were great at reflecting UV radiation, and this was totally unexpected. So if you have a look at the bottom right-hand graph there, each of those lines peak at a certain point where that particular percentage mixture of tunicate CNCs reflects the most amount of light. And so the bluey-purple ones, which are from 10% onwards, they peak in their UV wavelength, so they reflect UV light. And so it's kind of thought that these CNC mixtures could have new uses, like protective coatings for things like eyeglasses, or maybe they could be used in things like food packaging or biomedical instruments. So I thought that was a pretty cool, neat little thing that these scientists found out.
All right, the sea giving us new technology every day. All right, now, David.
Yes, how abundant is phosphorus in the universe? Astronomers from the School of Physics and Astronomy at Cardiff University have been working to find out. What is phosphorus good for? Well, it's absolutely necessary for life, as we know it. As it is used in the body as a phosphate. That is a polyatomic ion, if you remember that from your high school chemistry. That is just a fancy way of saying that it is a molecule with an electric charge, in this case -3, courtesy of its oxygen atoms. Now, when it comes to biology, chemistry is destiny, and phosphate has very useful properties that render it indispensable to life as we know it. The reason I'm emphasizing this, of course, is because the life on our planet is the only life we know about, so that limits us as to our understanding of life. But phosphorus is so darn useful that I, for one, would not be surprised if all life required it. Also, even though there may be other forms of life out there, they, by definition, would only have access to the same chemical building blocks that we do, and that sets limits on what is possible. Chemistry is destiny. Phosphate groups also form part of the backbone of the DNA molecule, that other part being a sugar called deoxyribose. They bond together, resulting in an alternating sugar-phosphate backbone. It is the specific properties of the phosphate ion that help give DNA its helical structure, as well as enabling it to be water-soluble as well. The nucleic acids that form the rungs of the DNA ladder are not otherwise naturally so. ATP, or adenosine triphosphate, is another really important organic molecule that uses phosphorus. This is the molecular energy currency of the body, and energy is stored and released by the molecule in the formation and breaking of the phosphate bonds. Phosphate can do this because of its 4 oxygen atoms bound to the phosphorus and still having a net charge. So now I have convinced you how important phosphate is to life as we know it. The natural conclusion is that in order for life to exist elsewhere in the universe, there needs to be phosphorus, and that is what brings me to the main topic of my story. Recently, astronomers from the School of Physics and Astronomy at Cardiff University have been using the William Herschel telescope to observe infrared light from 2 supernova remnants, the Crab Nebula and Cassiopeia A. They were specifically looking for iron and phosphorus. I've already discussed phosphorus. Iron, of course, is also important for, amongst other things, making up the core of a planet if you want it to have a magnetic field, but I digress. The results of the comparison were surprising. They found much less phosphorus in the Crab Nebula than Cassiopeia A. These results are preliminary, and they've asked for more telescope time to look at the nebula again to check if they missed some. But the implications of these findings are that phosphorus just lying around in abundance when a nebula begins to collapse to form a new star system where life can potentially arise is not a foregone conclusion. It might very well depend on you being lucky enough to be part of the right kind of nebula, one that received material from the right kind of supernova explosion, one rich in phosphorus. Dr. Greaves said ominously, the route to carrying phosphorus into newborn planets looks rather precarious. We shall have to wait and see if we can learn more about phosphorus abundance in the universe. In the meantime, be thankful that a supernova billions of years ago and far, far away died that you might live.
All right. Phosphorus. Can't get enough of it.
We need a lot of phosphorus. It's important stuff.
All right. Now, Lisa, I think you had something about solar water filter.
Yeah, so research that was published just 2 days ago on May 3rd in the journal Advanced Science, researchers found a way to harness the power of the sun, to filter water with near perfect efficiency. So I'm really excited about it. They actually modified the design of something called a solar still. And solar stills have been around for hundreds of years. You can basically make one yourself, like with some plastic sheeting, a couple rocks. It uses the power of the sun to heat up water so that it evaporates into water vapor. This water vapor is purified and you collect it by letting it condense or turn back into a liquid. And if you built your solar still correctly, then you can usually collect that purified water away from contaminated water. But the problem is that these designs aren't really that efficient. They take in the heat from the environment and heat up and then lose that heat back to the environment or surrounding air and that heat isn't used to evaporate the water. But now researchers have come up with a way to keep their solar stills cool. And they've done that with some pretty cool design. They used paper coated with carbon and placed it in a triangle roof shape with both ends draped in water. As the water traveled up the paper through wicking, it gained heat and evaporated, causing even more water to be drawn up. And by laying the paper at this steep angle, it received less direct sunlight than if it was laid horizontal, which helped keep the paper cool. And you can see in this image that the flat version, or image B, got as hot as 42 degrees centigrade, whereas the sloped versions were much cooler. Only the 22.4 degree slope only reached 25.6 degrees Celsius. And the researchers actually achieved an evaporation of 2.2 liters of water per hour per square meter of the device under one equivalent sun of light. And PhD graduate Hao Min Song believes that if this technology is upscaled to the size of something like a mini fridge, it could generate 10 to 20 liters of clean water every single day. But I think the coolest thing is that by using low-cost materials, this technology could be a real alternative to water filtration for people in need. And they've even got backing from the National Science Foundation's Small Business Innovation Research Program. They've created a startup called Sunny Clean Water to bring it to the people who need it the most.
All right. Okay. Now we're going to take a quick break and then we'll come back with Jade. Thank you, everybody.
We've always looked to the stars. They guide us, give us comfort, help us find our way. We see ourselves out there. When we look up, it inspires us. And we long for something we don't yet know. We yearn to go there. So we venture forth.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills.
Tranquility Base here. The Eagle has landed. It's one small step for man, one giant leap for man.
The exploration of space will go ahead, whether we join in it or not.
Many think we stopped exploring. But we know our journey didn't end.
T-minus 1 minute.
We've only just begun.
Orion is functioning perfectly at this point.
Come with us and explore tomorrow.
Hello and welcome back to The Conversation. Before we dive into our main topic, we'd like to give a huge thank you to our escape velocity citizens. We also want to thank our orbital citizens. These people contribute $5 an episode. In return, they get their name in the second and third segments of the show, voting rights on upcoming roundtable discussions, free worldwide shipping from our TMRO swag store, and so much more. Every bit helps, and we wouldn't be able to continue making these awesome shows if it weren't for you. So for a complete list of rewards, or if you would like to become a citizen of tomorrow, head on over to patreon.com/TMRO. So today, I am joined and honored to be speaking with Dr. Maria Helena Braga. She's the engineering professor from the University of Porto in Portugal, as well as a research scientist at the University of Texas, Austin. She's also a senior research fellow at the Materials Institute, headed by colleague and lithium ion battery co-inventor John Goodenough, where she is currently expanding our understanding of solid glass electrolytes and glass batteries. Hello, Dr. Maria Helena Braga. How are you doing today?
I'm fine. Thank you for inviting me. It's a pleasure, and I saw so many interesting things in the first part of this program. I congratulate you because I started with magnetic fields, exactly analyzing the rocks. So it's very interesting for me, and all the other interesting small programs that you have presented here. Very, very interesting.
Well, thank
Congratulations.
you. Oh, well, thank you so much. That definitely means the world to us. We're glad you tuned in for the news segment. So I guess as we get started, I think it's important to ask, what is a solid-state battery and how does it improve upon our everyday lithium-ion battery?
Okay, so let's start by what is a battery. A battery is composed by two electrodes in which the ions and electrons react, and with a compound that makes the electrodes, and it's made by an electrolyte, which is more or less like a carpet to ions. And where the electrolyte is a very bad conductor of electrons, because we want the electrons to go through the external circuit to give energy to all our appliances, for example, our computer. So we don't want the electrons to go through the interior of the cell. Now, in a lithium-ion battery, that electrolyte, which is that so-called carpet for the ions, is liquid, and it's a flammable liquid. So it happens very frequently that this flammable liquid, because some dendrites, which are kind of branches or swords that go from one electrode to the other, they grow inside your battery. They form short circuits for the electrons to go through inside the battery. And when the electrons cross the battery heats up. And because you have a flammable liquid, the explosions can occur. And we have heard about a lot of explosions.
Absolutely.
So to overcome that problem, the idea is to substitute the liquid, the flammable liquid, organic liquid, by a solid-state electrolyte.
Fascinating. Okay, so, and I think that brings me to my next question, which I actually did already see in the chat here. So WKD actually asks, why aren't lithium ions good enough anymore? Now, I know you just listed a couple of potential risks with using these batteries, but is there like a big overall reason why we would need an improved type of battery, like an overall different design of it?
So the first reason I would say is safety, as I was telling before. All lithium-ion batteries have to use an organic liquid electrolyte because lithium cannot be in contact with water, because otherwise it would explode. So you have to use an organic electrolyte. So the first reason is this safety reason, because you cannot overcharge the battery. Otherwise, if you overcharge the battery, you start forming. There are other spurious reactions that occur in your electrolyte, in your battery, as we are seeing all these dendrites grow, these kind of branches in our left side of the image. And they can go through the separator that separates the two electrodes. And when they do, they are the perfect pathway for the electrons. So they don't go through the external circuit. They prefer to go to the short circuit. They are like us. They use the law of the least effort. So the electrons will go through inside the battery, and then this may cause an explosion, because we know you are in agreement with Ohm's law, and there is another law that says that Joule, that if you have a low resistance in your cell, a high resistance in your cell, you are going to form a lot of heat. So the electrons will go through the cell and there will be a thermal runaway and an explosion. So this is the safety is the biggest issue. The other issue is that the lithium-ion battery of today has evolved almost as much as it can evolve. So we are achieving the almost 100% of the capacity or energy density that is directly related with the capacity of the battery. So for these type of cathodes or positive electrodes that we use in today's lithium-ion, you cannot increase the capacity anymore, or there's just a small amount of left to increase. So the improvements in the lithium-ion battery are just engineer improvements. So at the surface and the contacts, and so it's not anymore a breakthrough or a step increase or a leap that can be done with lithium-ion. And they are just determined, the capacity is determined by the cathode. So we cannot improve much more the energy stored in the lithium-ion. So that's why we want a new battery, because it's not enough, the energy that we store in the lithium-ion.
Absolutely. So you mentioned breakthrough, and that brings me to my next question. I understand a lot of your research was in materials science and engineering. So I have to ask, what was the breakthrough for you and your team in developing the design of using glass or developing the solid-state battery?
So actually, I'm a physicist. So we were, and Professor Goodenough is also a physicist. And when I started to work in Portugal in the glass, the most important property for me was actually the high dielectric constant that the glass has, not how fast the ions are conducted in the electrolyte. So let's remember that the electrolyte is like a carpet for the ions. So they have to be conducted in a fast way so that we don't lose the energy to conduct them in a battery. But in a capacitor, that is, instead of an electrolyte, we use a dielectric material. This means it's a material that can form molecules that are polar. So they have a zone which is more negatively charged and a zone that is more positively charged. Let's imagine like water, for example. And so if the material is what we call ferroelectric, so yeah, exactly. In the electrolytes, here in a conventional battery, you have what people are worried about is the conductivity of the ions in the electrolyte. So how fast they are conducted in the electrolyte, so that no energy is lost or a minimum amount of energy is lost. In our case, we use the capacity of a dielectric material, which not only has fast ions, but also has dipoles that can align and form chains that are aligned with the electric field. And so this is the principle of how a capacitor works. So they actually, the charge is conducted through the alignment of the dipoles. So this gives an extra surface charge that has to be compensated at the interfaces. So this is very important. This would be the breakthrough for our batteries, is that not only they have ions that are conducted in a fast way, but they have these dipoles as in a ferroelectric material that can align and bring an extra surface charge, which is going to create other phenomena inside the battery, like the possibility of charging a supercapacitor inside the battery, like at one interface in the battery. This is a little bit difficult to explain without our figures, but I hope you can understand that besides the usual electrochemical energy that is stored in a battery, we can store electrostatic energy like in a capacitor. So this is mainly the important message, or what we think it's important is the breakthrough in our technology.
Absolutely. Well, thank you so much for explaining that. That certainly does have like a lot of really amazing implications. And obviously there's a long list of positives with these new batteries, such as longer battery life, higher energy density, not blowing up in my pocket, which is always a plus. But there's a question in the chat that I was actually going to ask as well from Hanny Sporwerp on Twitch. They ask, what are the qualities of solid-state batteries other than safety? Can they be quick charged safely? Also, what are the downsides? What are the potential complications from these new batteries?
So, very good question, actually. Usually, solid-state batteries can only be used at around 50, 60 degrees C because the ions are not as fast traveling in the electrolyte as in the liquid. And we can understand this. The diffusion across a solid is usually slower than across a liquid. So what happened? The problems with the solid state batteries is usually related to this. What the people do to overcome this problem is that they make thin layers of electrolytes, so that the thickness is, of course, smaller, and so the ions don't have to travel a long distance, so they don't spend energy by traveling. So this is the downside of a solid state battery. But if in our case, if in a battery you have these chains that can align, then the ions don't have to travel all through the battery. You have the ferroelectric possibility as in a capacitor, and so the ions only do small displacement in the battery. So we can use these batteries not only at room temperature but at lower temperatures as well, because we have that extra, which are the dipoles that align and connect, like they make the connection between the two interfaces of the electrodes, and they make the connection of the charge between the two interfaces. So the ions only approached one interface and get away from the interface, but they don't have to travel all the way through one side to the other, from one electrode to the other. Also because our electrolyte contains a lot of ions. So if the ions start to plate, which means react with the electrons on, for example, the negative electrode, they don't have to be immediately replenished by the ions on the cathode, which is what usually happens in a battery, because there are a lot of ions in our electrolyte. So these are advantages that allow the possibility of working with our batteries at low temperature.
Awesome. So, so we've heard about kind of how this improves upon, our everyday lithium ion battery, but what are kind of the implications for these improved batteries? Obviously, everybody wants a battery that lasts longer, especially when it comes to cell phone use and whatnot, but what about transportation? As I understand from some of my research, is that this can have huge implications for kind of transitioning more into green energy vehicles. So what types of implications would this have on the broader scale?
So of course, we are still at the coin cell level. We need to make, actually the industry needs to make the scale up. But we are very confident that the scale up is going to be possible. So what do you need in a car? You need a battery that charges fast and that can be auto-sufficient for a long pathway, for a long run. So for being auto-sufficient for a long run, you need to have a very high energy density or capacity to store electrons and ions in your battery. So as in our case, because we not only have the electrochemical storage like in a normal battery, but we have the electrostatic storage as in a supercapacitor, we have an extra energy that can be stored in one of the batteries, the one that we think would fit better for a vehicle, because we are studying different kinds of batteries or different kinds of architectures. But for the car, I would say that this is what happens. We have the electrostatic as well as the electrochemical component. So that kind of doubles the electrochemical component. So we have a high capacity. And on the other hand, you need to charge fast because you don't want to wait for a long time in your station, even if they are very nice and you can have a coffee or or some cookies and rest a little bit. You don't want to wait there for a long time. So you want to charge fast your car. So as I was saying, because we have the electrostatic component, we can charge fast at least that component, and this makes the battery very attractive because we can charge it fast, and this is one of the important issues in batteries for cars.
Absolutely. So you did mention that they do work in lower temperatures, and actually we have a question from our very own Mini Soj, and she asked, would they be well suited to work on Mars, which is extremely cold and would experience extremely low temperatures?
I think that from Mars we still have to improve a little bit more. Mm-hmm. Well, what I can say is that we are making experiments at -20 degrees C, and we can work with them at -20 degrees C, and eventually at -30. But that will not be eventually possible to work on Mars. Or I think that we would still need to come up with another breakthrough, or all the other researchers that are studying batteries.
Awesome. Well, it's a stretch goal, but I'm sure we'll get there someday. So there's a really good question from WKD, and they ask, have you found any commercial partners already to assist with development and getting this on shelves at stores?
There are a few industries and other partners in negotiations, and we have already started to work in research with some, but I cannot be very deep into this because this is University of Texas issue, and I don't want to go further.
Absolutely. Definitely understand.
Tell more about this.
But it's good to know, and it gives us hope that there is some traction there and that there is going to be further development. And that leads me to my next question. How long do you project it'll take until these hit the mainstream market and we can actually see them being used on a bigger scale? From what I understand, lithium-ion batteries originally took over a decade before they became commercially available. So using your future predicting skills, how long do you think it'll take for these?
Of course, I don't have a crystal ball. I would like to, but no. Well, I think this depends much more on the industry than it depends on us, because what we do is that we work on the concepts. We make coin cells, and we develop the strategies and the architectures and try to understand how the batteries work and what are the principles underneath how they work. But the develop, so the scale up, making them big and make all the tests that need to be done for a commercialization, especially in vehicles. This has to be done by industry. This is the purpose of the industry, not the purpose of researchers at a university. So we are trying to go as far as we can go, but our main motto is to make research, and the development should be made by the industry. So it depends on the industry. If the industry has a lot of skilled scientists as well, and they have the proper tools and so on, this will be faster. If not, it will be slower, but hopefully it will come out.
Absolutely. Well, Dr. Braga, thank you so much for speaking with us today. Where can viewers go if they want to learn more about solid-state batteries and the progress of them?
Well, that's a good question. We are actually, we will have a site in some months.
Oh, wonderful.
But so far we don't have an updated site, but they can study, they can go to the papers, even if it's for, for more technical detail. But I think they can search for our names and see our papers.
Absolutely.
This would be what we have right now.
Definitely.
But in the future, we will have a site where we put all the news and more details.
Well, that's exciting. I look forward to seeing that. But yeah, absolutely right. You Google any sort of either solid-state battery or Dr. Braga, and there's a wealth of journals and all sorts of wonderful resources that you, the viewer, can actually go read into. Believe me, it's a fascinating topic. I had to read everything at least 3 or 4 times before I kind of understood it. But once I kind of grasped the meaning of everything, it's absolutely fascinating, extremely exciting. So thanks again so much for joining us. You definitely enlightened us and helped us understand everything so much better, Dr. Braga, and we are so excited to hear about the progress of these solid-state batteries. So thanks again for joining.
It was my pleasure and my honor, and I see that you have a wonderful, fantastic project, and keep on going like this and making all these spots. We need to talk about science to everybody, and it's very, very interesting. Congratulations! You are the ones that should be congratulated.
Oh, thank you. That means the world to us. So stay tuned. We will be back after a short commercial break to answer your comments from the last show. So we'll see you in just a bit.
Science. It both draws us together and tears us apart. Brings discoveries to cure us and threaten us. It is neither good nor evil. It is what we decide to make of it. There is so much more to learn, and we are curious. Together, let's explore the science of tomorrow.
Welcome back to the conversation. Before we get started on last week's comments from last month's show, we are going to give a huge thank you to our escape velocity citizens. We want to thank our orbital citizens and, of course, our suborbital citizens. These people contribute $2.50 per episode. In return, they get their name in the third segment of the show, free U.S. shipping from our TMRO swag store, and so much more. Every bit helps, and we wouldn't be able to continue making these awesome shows if it weren't for you. So for a complete list of rewards, or if you would like to become a citizen of tomorrow, head on over to patreon.com/TMRO. All right. So last month on our show, we spoke with Guy Trudell, MD, from the University of Ottawa about the marrow experiment. All right, so we've got some comments about that. Actually, sorry, this first comment is from YouTube, and it's FPV Reviews. Okay, it hardly matters, but just for the record, taking a breath sample first thing in the morning must refer to the waking time for each astronaut and not for the actual morning aboard ISS, which there would be approximately 19 for every Earth day time equivalent. Okay. Does anyone have any comments on that segment?
So I think this one is referring to, so with the marrow experiment, the astronauts or the subjects actually had to give a breath sample as soon as they woke up in the morning. It had nothing to do with like it was when they woke up, not when like the ISS passed into like wake up time or Houston wake up time, anything like that. Because like if you're not aware, the ISS does go around the Earth. Like you get 15 sunsets and sunrises every day because it goes around the Earth so quickly. So you don't have to do 15 breath samples for this particular experiment.
They don't have to go to bed every time it goes around.
It's like 15 nap times. It's epic.
Oh man,
you're like the shortest circadian rhythm ever.
All right. Oh.
All right. So then, yes, FPV Reviews. It was about when the astronaut woke up first time. All right, we've got another comment from AZ Off-Roadster from YouTube. Okay, getting a bone marrow sample from the pelvis is not as bad as some say. It's no picnic, but I felt worse. Not asking why. The doctor that took mine was a small Asian woman. She needed to call in help to actually get the needle in. You're not selling me on this.
Yeah, the fact that you would need more than one human strength to get a rather thick needle into me bones doesn't exactly sound like a walk in the park, but you said it's no picnic.
Yep, puncturing bone with steel.
But cool. Hey, this person's felt worse. So we don't know. This person could be like Wolverine status pain.
Right, every time.
Yeah, like he's like gone through some stuff. Right, so this was like nothing.
I got you.
Yeah.
But it sounds like it's still an important thing to do, getting the bone marrow samples. So it's good that it's not the worst thing you'll ever feel. So let's have it done.
I mean, unless you've like never experienced like, you know, like, oh my God, my arm got chopped off type of pain, in which case I'm sure getting a marrow sample extracted is an experience to be had.
Right? Probably childbirth, but this doesn't sound like it comes with the oxytocin wash after, so there's no, okay,
and you can't get an epidural for that. All right.
All right, our next comment is from YouTube, Francisco Pinto. It's a great episode. Congratulations for the interview. It was really amazing. I'm looking forward to watching the interview with Dr. Maria Helena Braga, Portuguese speaker like me, although she is Portuguese and I am Brazilian. We love your shows down here. Thank you so much. Thanks. We love doing them.
I hope you enjoyed it. I hope it lived up to your expectations.
Hi, Brazil.
Hello, Brazil.
And Portugal, why not?
Portugal's beautiful.
All right, and we know all about batteries, or at least solid states.
Yeah. Woo.
Okay, another one from YouTube. We have LBCG. Okay, this one's a suggestion. If you feel like there's loads that can be said and your shows are too far apart, then once every 2 weeks maybe? Or I say that knowing it's a lot of work and a long day, so whatever's best. Okay, is this about a comment that happened last show? We've got so much stuff we want to say.
It must have been during After Dark. That's when we had a whole conversation about everything.
Wanting to do more, overachieving.
I would love if we had a show every 2 weeks. And you know what? That's the whole point of like bringing on, you know, Sarah and David and expanding the cast. Because, Yeah, and also thank you for coming on the show. I know it was really last minute, but you guys have done an amazing job. And yeah, the whole reason that we're bringing more people into the show and training everybody and cross-training everybody and making them feel uncomfortable with roles they've never done before at the last minute is so that we can train our cast to have enough people to be able to spin up more shows and have them going every few weeks without absolutely exhausting everybody. So that's kind of reasoning behind that. And I hope eventually we will get to have a science show every 2 weeks, hopefully when I finally get back to the US. But yeah, that is the ultimate goal. The ultimate goal is weekly, so we'll get
daily, hourly. We'll never
Non-stop
stop.
coverage. All right. LBCG had another suggestion. Oh, one more suggestion, although it could be a lot of work. How about visits out to actual labs and discussions with scientists there? You can call them science documentaries or something else. Copyrighted. All right. It could make for interesting shows, and you can shoot footage on location for great visuals.
That would be epic, like little field
Absolutely.
trips.
I know. I'm down. Let's pitch it to Ben.
Hey, Ben. How do you feel about that? Oh, no, that would be...
Hey, Ben, this is happening. You get no choice in the matter.
I know, right?
It's decided. Lisa just said.
We're just going to do it rogue. We're going to just do it live.
Tomorrow
Just get there.
Rogue.
We'll
Like
do it
NASA
live.
Rogue.
Do it live.
There you go. Yeah, no, that would be amazing, especially if we went out to like some really neat labs or, maybe a JPL visit here and there. It's still on the street, basically.
Just pitching.
And
JPL.
just
we're coming
saying,
at you. Yeah.
I think it'd be neat.
Yep.
I like this comment. I don't think it'd be too much work. But then again, I'm not the technical person, so I could be like getting my eyes rolled out so hard right now. Let's just show up and talk to people. It's not that much work.
And again, this all comes down to, having the shows grow and expand. And one way that we can do that is by having more resources. And that's where, the crowdfunding comes in. The bigger that our supportive network gets, the more things we can do and the cooler stuff we can do. With science, we can go into labs and we can do stuff on location. With space, we can do live launch coverage. But it all comes down to having those resources, and which is why we're so grateful to all the crowdfunders and citizens of tomorrow that we have at the moment too. So, and even if you can't contribute, with money, sharing the show helps a lot as well, because then we can reach greater audiences, and maybe that will help us get more resources too. So,
Yeah.
thanks.
Never know if we get set in front of the right pair of eyes, and then all of a sudden, bam. Private investor, billions of dollars, all of a sudden we're on Mars. I mean, it can happen.
No?
It can happen. Just a must.
All right. So thank you, LBCG, for the great suggestions. We're working on it, and you can help. All right. Okay, so next month, we hope you will come back for our interview with Alex Moss, CEO and founder of Canaria Technologies. They're building wearable tech to fight fatigue-related workplace injury and medically monitor astronauts in space. That sounds exciting.
I mean, I'm already hooked.
All right, well, it's a good thing you'll be doing... No, I'm just kidding.
All right, by the way.
Okay, so before we go, we do want to recognize our ground support citizens. These people contribute $1 per episode. In return, they get access to After Dark as soon as it's posted on demand, access to our exclusive citizens-only hangouts, and so much more. Every bit helps, and we wouldn't be able to continue making these awesome shows if it weren't for you. So, for a complete list of rewards, or if you would like to become a citizen of tomorrow, head on over to patreon.com/TMRO. All right. Thank you, everybody.
Thank you.
And signing off.
See you next month.